All right. Well, hey everyone. Let me share my screen real quick. Um, Kind of play this. All right. So can everyone hear me?
Yes.
Yes? No, thank you. Hey, I'm going to be talking about programming quantum computers today. And so the reason I want to give this talk is because I've been following quantum computing for some time now, reading just mostly like popular science articles and things like that. And I'm a programmer, and I kept getting kind of frustrated by the fact that, I'd learned a lot about how computers are built and things like that, but nothing really about how you program them. I wanted to know, like, how would you actually implement an algorithm? What does that look like? What are you actually doing when you code it? And so I put this talk up on the board, and I figured I would do a little research, just enough to kind of satisfy my curiosity, Dunning-Kruger my way through the talk, and that'd be it. But turns out I did a little bit more research than that, and mostly what I found out is why you don't talk about programming quantum computers to general audiences. So this talk is going to be a little rough, and I'm going to try to sell it a little bit, and then I'm going to explain why maybe you don't want to stick around for this talk. So why you want to stick around? So quantum computing is cyberpunk as heck. It's basically like a kernel exploit in the operating system of the universe. It allows you to steal computing resources that just should be illegal under normal rules of computer science. You can't get that far into it without talking about parallel universes and stuff like that. It's really, really, really cool. I'm a math, physics, programming, science fiction nerd, and it kind of like hits all my buttons. I don't know about you. Also, quantum computers, as they've been built so far, are really, really beautiful. It's not really relevant to this talk, but I wanted to have the second slide. All right, so why would you maybe not want to stay around for this talk? It's going to get really mathy. And this is actually the answer to a homework problem that I didn't do in the course that I took on this. I thought about just emojiing my way all through the math like I did in my last talk. And the thing is, quantum computing, or quantum mechanics, there's no real intuition to it. You can't really talk about it without the math. It doesn't make any sense. And I was really worried that if I just didn't put any math into it at all, it was going to just be one of these talks that I got so frustrated about in the first place. So I'm going to sling a bunch of math at your mind walls, and we're going to see what sticks. And fair warning if that doesn't seem like your cup of tea. All right, let's get started. So a quantum computer is really made of two parts. It's made of something called qubits, which is like the memory of the computer, and quantum gates, which are kind of like the operations or actions of the computer. I'm going to talk about qubits first. So a qubit is much like the bit that we're all familiar with. It has two states. Like a classical bit has two states, 0, 1, on or off. A qubit has two states, which we label 0, 1. They have these brackets around them. I'm not going to explain what those are, but I will say that are a little bit different in the sense that they're actually vectors, and the 0 and the 1 state are actually orthogonal to each other. So we can kind of think of them as, they kind of rotate into each other and things like that. And we'll talk about that a little bit more. So where qubits are different from classical bits are they can go into something called superposition. And what this really means is the bits can be simultaneously in one state or another, at least in a certain sense. What they actually have is an amplitude that describes how much in one state they are versus the other. So while they're in the quantum state, they have this amplitude. When we actually measure them, they have to be in one or the other. They're always 0 or 1. But while they are in the quantum state, they have these amplitudes, and those describe the probability that they'll go into one state or the other when they get measured. And unfortunately, these magnitudes, these amplitudes are actually complex numbers. And the complex numbers, it makes the math more difficult, but it also gives it this kind of interference that you might know a little bit about from quantum mechanics. We'll talk about it a little bit. And that interference gives us nice things like chemistry. All right, so the other big thing about qubits is that we can combine them. So normal classical bits, we combine them together and we get multiple states. So if you have 3 bits, you have 8 states. I think we all know it's just the binary counting. I think we kind of understand how that works. qubits, we get the same kind of proliferation of states, but again, it's in all those states at once, at least some part of those states at once. And so if you have 100 qubits, you end up with 200, can have 200 or like 2 to the 100 states, which is a really, really large number. And it's this ability to be in so many different states at the same time that really gives quantum computers the power. Okay, so now I'm going to talk a little bit about the other side of it, the actions that you perform on it. Oops. Okay, so I'm going to show you a lot of these quantum circuit diagrams. The way these things work is we have all our input states on the left here. These are the states of the qubits going in. In this case, they're all zeros. That's actually pretty common. And then the way we read this is across each one of these lines represents the kind of path of one of these qubits and the transformations it takes along the way in the calculation. At the end of that calculation, we're going to measure it almost always, not always, but almost always, we're going to measure it. And then at the end, it's going to be in some definite state, 0 or 1. Over here, while it's in the quantum computation, it could be in superposition. Okay, so this is our first gate. It's called the poly X gate. It is really just a knot. So if we take this qubit, feed it in as a 0, we'll get a 1 when it comes out. If we feed this one in as a 1, it's going to come out as 0 when it comes out. So it's a pretty straightforward gate. We have a few more gates that are like this. So this one's called a controlled knot. And the way this works is if you feed a 0 into it, it does nothing. And the other qubit goes through and it's just whatever it was in the beginning. If you feed a 1 into this one, it acts like the NOT gate that we saw earlier on the second qubit. And so if this is a 1, this one's going to flip. You can see it goes from 0 to 1 here. This is called a Toffoli gate. Now, remember, all these gates actually have to be implementable in a quantum computer. So we only have a few gates that really we can work with. This is one of them. It's very similar to the first one. The only difference is that it takes 2 control inputs. So if these are both 1, then this one will get inverted. Otherwise, nothing will happen. And if you're looking at this, you might, if you've done digital circuits before, you might kind of recognize this. That's good. This is a digital circuit, a classical digital circuit for something called a full adder. And the way this works is you pass in 2 bits and a carry bit. And then what you get out of it is a sum of those 2 bits, or actually the 3 bits, and a new carry bit. And you can actually chain these together to create like addition over some kind of large number. So this is the full adder as a quantum circuit. And so these are just the gates we saw before. We're passing in 2 qubits in some state and a carry qubit. It goes through this calculation. In the end, we're going to have the sum qubit on this 3rd qubit and or the sum state in this qubit and the carry in this qubit. So they work very similar, at least sometimes very similarly to digital circuits. And this is what it looks like in code. This is actually in a language called Q#. This is Microsoft's quantum computing language. There are several of these languages out there. They all kind of work the same way. What this is like a full-fledged computer language. It works pretty much like any other computer language, except it has these commands like CC0 and C0 and M, which are actually going to end up making API calls or something to a physical quantum computer and set up the gates the way they need to be, put all the qubits in the right state, initial state, run the quantum computation, and then run the measurement. And then those measurements are going to come back into the program, and then you can continue the calculation on this program. I don't think that this, like looking at the code like this, actually adds any insight over the diagrams I just showed you. So I'm not going to show this again, but this is actually how you, like if you were programming a quantum computer, this is what it would look like. Okay, so now I want to get into a little bit more depth about what these gates are. They're actually matrix transforms. And so the NOT gate is just like, it looks like an identity transform, so if you invert it, and kind of see that's happening a little bit with all of these. So if you squint a little bit and you've ever designed digital circuits, you know that the way you do it is you work with truth tables. And so you want to design a function as a digital circuit. What you do is you first create a truth table that tells you how to map all the possible inputs of the function into all the possible outputs. the true false values of all the possible outputs. And so we do exactly the same thing here. If we want to design a function or create a function as in a quantum circuit, the first thing you do is figure out what the transform is going to be, what the matrix transform is going to be. And then you figure out how to combine these gates. And there's an algebra how you combine these gates to create a matrix that's going to be the transform. And there's actually going to be lots of ways you can combine gates, and some of them being more optimal than others. But there's ways to do it to create this larger matrix. And of course, you can use a computer to kind of figure out how to do it for you. If you have that matrix, you can just kind of let the computer work backwards for you and come up with something optimal. Okay, so it's been kind of straightforward up until now, but the thing is, that's not all the gates. There's probably about, 10 gates that we talk about with quantum computing, and like a lot of them are more common, much more common than the other ones. There's this H gate, the Hadamard gate, that we're going to talk about in a bit. You can also see there was an X gate, now there's a Y gate. The Y gate looks just like the X gate, except for it's imaginary and negative. That's kind of weird. We have this RK gate, which is this little guy down here, also looking a little messy there. And the thing you got to understand about gates is it's best to think of these all as rotations. There's something called the Bloch sphere, which is this diagram, which represents the state of a qubit. And we have the 0 state at the top and the 1 state at the bottom. And so all the gates we've seen so far are really rotations from the top to the bottom or the bottom to the top. But it can actually be, because it's got those complex amplitudes, it can actually be in a lot of different other states. And so we can also rotate through those. And that's what these gates are doing. And we also don't have to go all the way from 0 to 1, which is what this H gate is doing. So let's talk about that in a little bit more detail. So this Hadamard gate is the most important gate in quantum computing. We almost always use it. And what it does is just does kind of a halfway rotation between 0 and 1. And so if you apply the Hadamard gate to a 0 state, it's going to take you to 0 plus 1, and there's a normalization constant down here you don't have to worry about. And then applying it to 1 takes you to 0 to negative 1. And when you take the amplitude of a state, it doesn't, it's basically like taking the square of it. The negative sign doesn't really matter at that point. It's going to have the same value. So these are both, it takes it to somewhere right in between 0 and 1. And I'll talk a little bit about that a little bit more later. All right now, actually. So this is what happens if you can only put Hadamard gates into a quantum circuit. We're going to feed in a bunch of qubits in the initial 0 state. And then we're going to apply the Hadamard gate to it. And what that's going to do is now each one of these qubits on each of these lines is going to be equally in the 0 state and in the 1 state. And as I mentioned earlier, the amplitude of how much it's in one state or the other gives you the probability it's going to be measured in one of those states. And since those probabilities are equal, those amplitudes are equal, then when we measure it, it's going to be equally likely to be 0 or 1, which means this whole circuit is just a big random number generator. It's not a useful quantum circuit, but it is very useful to get it into this state. And we'll talk a little bit more about that in a bit. Getting back to like just kind of fleshing out the idea of a qubit, if we do these Hadamard gates and then we apply some gates that cause the qubits to interact, all these qubits are going to be entangled. And so now we have the kind of full quantum computer with entangled states that gives us all the power that we're looking for. Okay, so that was kind of like deep down, like how you actually get into the detailed programming of a quantum computer. I'm going to raise it up a little bit and talk about how we like actually would create a program and think about a quantum computation and a little bit about how it works. So we can do this in a few steps. We're going to start off by putting all our qubits in an initial state. These are going to be 1s or 0s. And this is just a garbage in, garbage out kind of thing. We need to know what the initial state is in order to get a reasonable answer, like to understand the answer when we're done. So we prepare the states. And then almost always the first thing we're going to do is rotate them using the Hadamard gate to put the qubits in superposition. And then we apply a digital circuit. And so we create, this is like, you can imagine this being our full adder that we saw earlier, It's just all those gates put together. It's just going to be a whole bunch of gates kind of lined up and interacting with each other on all these lines. And so the idea here is this is a function or a computation that we want to perform. And it's sometimes easier to think of it as actually a function that we want to solve or, or analyze. But something pretty incredible is happening here. What's actually going on is we've rotated all these qubits into the 0, 1 state, the superposition. And so what's going to go into this function is actually both 0 and 1 for all these inputs. And that really represents all the possible inputs that could go into this function. And all these quantum gates preserve that superposition. So what you get out of the function is actually all the possible outputs of the function. And that is kind of amazing. I mean, because like I said earlier, if this is 100 qubits, you have 2 to 100 possible function values that are going to be kind of in the computer ready to analyze all at once. And 2 to the 100 is just this fantastically large number. It's actually, this is where we get into parallel universes, because like if you actually had that much information in a small space, you'd cause a black hole. So you got to explain that somehow. It's just amazing. But the problem with this is we have all those possible outputs from this function. If we now measure it, we're only going to get one. We're only in one universe or the other. So there's only one possible way this can come out. And that means we don't, that doesn't give us really any insight into this function at all. We haven't solved it. So we need another step. And that step, I haven't really heard a good term for it. I'm going to call it like an interference operator. But always what you need to do at some point is you need to figure out some way to cancel out everything that you don't care about, so that you end up amplifying the possible solutions that you do care about, so that when you measure it, you're going to get one of those and not something that you don't care about. And so this is the real trick of quantum computing, and it's not easy. It gets pretty mathy. But if you can figure out a way to do this on this function, you can do incredible things. And that's what quantum computing is all about. After that, it's pretty simple. You transform it, you rotate it back using a Hadamard gate to kind of get it back into it. So you're going to measure a 0, 1 again, and you measure, and then you get an output state. And then generally, this output state is either going to be something that is the right answer, like with really high probability, or maybe it's something that's just somewhat high probability, in which case you have to run it a bunch of times and kind of see, like, until you get it, kind of figure out whether it's right or not. Sometimes it's just one piece of the puzzle, and you have to run it a bunch of times to get all the other, or run different computations a bunch of times to get different pieces of the puzzle. So generally what we do is we're going to throw all this back into a classical computer. We may have to do some additional processing on the output, and then that is going to set up another experiment, another quantum calculation, and it will run it a few times until we get the answer that we're looking for. And this is at a high level what all quantum computation looks like. And I know this is ugly, but I wanted to just kind of like provide a little bit of insight into this kind of interference operator I was talking about. So if you apply a Hadamard gate over a bunch of states to a function, what you get this expression. And you don't have to worry about this. That's a normalization constant. You also don't really have to worry about that. But if you see here, you got a sum over a bunch of basically all these possible states. And that sum has got this -1 to some function. And so if you take a -1 to an even number, it's going to be 1. And if you take it to a negative number or an odd number, it's going to be -1. And so if you can get those things to line up, you can see that you can get them to cancel out. And then you make it so that the things that you don't want to cancel out don't do that, or are the same, have the same sign. And this is how some of them actually work. And so I just wanted to kind of show it's possible to do that, and the kind of thing you would do to make it happen, but don't have to worry about this too much. All right, so now I want to take it up another level. I want to talk about an actually useful algorithm. Schrdingers algorithm is the most famous quantum algorithm out there. I'll talk a little bit about why. So Schrdingers algorithm is the one that it's why we worry about quantum computing and cryptography. RSA key exchange relies on taking two large prime numbers and multiplying them together to get a some composite number n, we can then pass around this n back and forth and then kind of use it with the primes to kind of figure out, basically it's how it works. But the thing is, if you could look at this n and figure out what p and q are, it would break the whole algorithm. The reason why we don't think you can break that n into p and q generally is because of something called the discrete logarithm problem. And it turns out that other crypto systems like elliptic curves, BLM, there's a bunch of things that kind of rely, at the end of the day, it's like, this is, when you analyze them, this is what it makes them hard, is the fact that like at some point you have to solve the discrete logarithm problem. And we don't think you can do that in classical computing, but we are 100% sure you can do it with a quantum computer. And that's because Peter Shor proved that you could and showed how to do it in the 90s. So I got to talk a little bit about abstract algebra here, just to kind of set the problem up. So you don't, like, Shor's algorithm doesn't directly, well, it does figure it out in the end, but this is how it goes about doing it. So if you're looking for these primes that multiply together to create n, you start off by picking an a, any a that's less than n, and then defining this function f of x, which is just a to the x, any x mod n. So the thing is, when you take the exponent of this number and mod n, what's going to happen is it's going to end up bouncing around in a bunch, and then eventually you can prove this, it's going to end up hitting some value that it's hit before. And then once it's hit that value before, the next one is going to be another number that's hit before and another number, and the function is going to repeat itself. It's a periodic function, and we call its period r. So if r is even and some other conditions, this is actually a pretty easy proof. I don't have time to go through it here, but if you look it up, it's not that hard to get from the fact that this repeats to the fact that that if you take this function a to the r over 2 plus 1 or minus 1, doesn't matter, and get the greatest common denominator of that and n, that's going to give you p or q. So you've solved it, which is great. And we haven't done anything quantum, but the problem is it's not easy to find that r, and that's that's the real trick. So how do we find r? Well, one trick we could use is Fourier analysis. So hopefully some of you have seen something like this before. What we're going to do is we're going to take that entire function, that a to x, and we're going to do a Fourier transform on it, and that's going to put it into its frequency space. So generally, that number is going to look, that function is going to look pretty random, but we know because it's periodic, it's going to have one frequency, which is that period. And so we're going to see a big spike here, and then another one at all its multiples. So we could just use classical Fourier analysis to figure out this problem. But the problem is Fourier analysis is an n log n, like that's a fast Fourier transform problem. And we've already said n is a very, very large number. So that's going to take, lifetime in the universe kind of thing. But by now, hopefully, if you've been paying attention at all, you're starting to suspect, oh, maybe we can just jam this whole thing into a quantum computer and make that work. And it turns out, yes, that's what we do. But you might be also wondering, how can we create this Fourier algorithm? We just saw, I saw a full adder, which just has 2 bits together, and that took like 6 gates. Isn't this like some kind of massively complex thing to create this Fourier analysis in a quantum computer? And it turns out it's not. And the reason why, this is the discrete Fourier transform. So a Fourier transform is just a basis transformation over the roots of unity. I don't expect you to know what that means, but it's really fun to say. But at any rate, this is the root of unity. That's what it looks like. And it turns out, if you remember that we had that R of K operator before, and that's a root of unity too. So it turns out quantum computers just kind of have this Fourier analysis built in, or something, like the building blocks of it. So it's not actually that complicated to build QFT, quantum Fourier transform. And this is what it actually looks like. We have our Hadamard gates at the beginning. We take these R2 gates, and each one has it's like a different root of unity. But We can do that, and then they're all controlled by all the qubits that come above them. So there's a lot of gates here. It's actually like, well, n squared over the number of qubits, but it's not that many qubits, so this is not that bad. And this is what Schrodinger's algorithm actually looks like. We take our original function, that a to the x, and then we analyze it by running the quantum Fourier transform on it. And then that's going to amplify that R value, or a function of that R value that we were looking for in the first place, and cancel out everything else. Then we rotate back, we measure, and then that function we're going to feed back into a classical computer. If R is not even, we're going to have to choose another A and redo the whole calculation and start over again, run it again. It's about half and half, whether or not you get an even R or not, so you don't have to do this many times. If it is even, then we can do that greatest common denominator trick in the classical computer and get our answer. And so that's it. I'm kind of running low on time, so I'm not going to talk about Grover's algorithm other than say it's probably more important than Schrodinger's algorithm. It's a little harder, at least for me, to understand. So I'm not going to be able to talk about it as well. And but Grover's algorithm actually can solve any problem in the class of problems in P, which is fantastic. It can do it in the square root of n time, which is not that fantastic, but still huge, considering that most of those problems would have to take n. So it's a quadratic speed up. But at any rate, if you're interested, I can point you at things you can read about it. But I think I'm going to stop there. And I have set up a channel in Slack, Quantum Computing. So I'm going to post the slides there. I'm happy to take any detailed questions there and talk about it. If anyone wants any learning resources, I'd be happy to talk about that, or just have, any general quantum computing questions. And I think I have a little bit of time for questions. So if anyone has anything they'd like to ask, I'd be happy to answer. I see Mike.
Yeah, so do modern quantum computers actually look like those things that you put up on that early slide, or are those yesterday's classic quantum computers?
I mean, I don't know about this month's quantum computers, but yeah, those pictures are recent, like this year. And I think one of them was at IBM. I think maybe all of those are at IBM. I don't know. Maybe one of them's at Google.
So you said Microsoft has this Q# programming language, and you can actually like run these things on their quantum computers. And so I'm imagining you've got these mega racks of like classical computers, and then in some other room you've got these like these sort of steampunky like shiny brass things. And is this like the old punch card systems where like you need to schedule time because there's only like one of them, or did they just have like football fields filled with like little shiny quantum computers?
No, they don't have football fields. I mean, yeah, the bad thing about Q# is you can run on a quantum computer, an actual quantum computer, but you got to run on Azure. And it's just a gimmick to get people to use Azure. They have these kind of, I think they're like 5 or 10 qubit machines. So there's nothing you can like super practical you can do with it. And since they're not very practical, I don't think there's a whole lot of contention to use them. But actually, I don't know the pricing model. So yeah, I do imagine you have to pay to use them. And then
But at the
you
moment,
should be able to.
It's a gimmick right now.
I think it's a gimmick. Yeah, I haven't looked into it that much,
Yeah.
but that's my suspicion anyway.
Okay.
Shannon.
Yeah, you want to talk a little bit about how close various institutions are at getting to like realization of this one of these algorithms in real life?
Yeah, I will talk about that. I don't like to talk about it because I'm actually a skeptic at the moment. I think the trick with it is people are really making these things with more and more qubits. I think the record right now it might be 56, but I think the goal is to get it up in the hundreds or even the thousands in the next few years, which sounds like like if that's all there was to it, Shor's algorithm, you know, you could break 256 bit encryption with that, or you know, like an RSA key anyway, which is 256 qubits, but or maybe double that. I'm not sure exactly, but the trick is error correction, which is the biggest question in quantum computing right now. You have to make sure that you don't, like, there's not a mistake that happens somewhere in the quantum computer. It's just like things have to be aligned right. And there's like, in normal computers, we just use redundancy, but there's this thing called the no cloning rule that means that you can't actually make anything redundant in a quantum computer. There is a way to do it. I don't quite understand how to do it, but there is a way to do it. But there's actually a mathematician has pretty good arguments to say that, like, as the quantum computers get bigger, you're just not going to be able to keep up, and the error correction is going to get away from you. So I think people that are actually building these things today are setting expectations for 20 to 30 years for anything practical to come out. Stefan.
So maybe one more question, but we are over time, folks. So just let's take one more question, and then maybe any follow-up questions after Stefano can go in the quantum computing channel.
Yeah, so maybe you were touching on this, but I was wondering, like, you talked about, I think it was before Shor's algorithm, you showed something that, like, you get a state that gives you an answer. It's either entirely correct, partially correct, or like probabilistically correct, and then you just run it again, right?
Yes.
So, right, so my question is, like, what is running it in, is that a stochastic process with memory? Is there like something like errors in the previous state might repeat at a certain probability, or is it like each time you're running it, there's an expected value that's reset?
I mean, I think that's definitely like valid, that maybe like there's going to be errors in it that repeat. That's part of the problem. But it's, when we talk about it being probabilistic, it's probabilistic at the quantum level. And this is like things happening randomly that we really just cannot access in our universe. It's like, you know, it's a very, very random process. And so we just expect it to get some answer, but we don't know which answer it's going to be. We can predict what the probabilities are. And so if we can predict the probabilities, we can do the statistics to figure out, like, well, you know, this thing now seems to be very, very likely to be the right answer. Does that answer your question?
Well, no, I'm kind of thinking, like, if you run it a number of times,
Mm-hmm.
you're running it like an infinite number of times. Is there some sort of, like, does it follow a particular distribution, or?
Yeah. I mean, that is like the way you actually describe it is that superposition over the entire state of the quantum computer, and all the amplitudes of those give you exactly the probability distribution that you're looking for. And so once you have that probability distribution, you can do the statistics to figure out, you know, like, is this a good answer or not? Is that better?
Yeah, I made way more questions now, but that helps.
Maybe we can take it to Slack.
Yeah.
All right. Thanks, everyone.